Valence electrons. Valence electrons are the electrons in the outermost principal energy level. And these are important because they are the ones that interact with other atoms, and so they are very important in how atoms behave, chemically and physically. It has to do with the number of valence electrons. So in those main group elements, the group number corresponds to the number of valence electrons. And the electrons that are not in the valence are in the lower energy levels. They're called the core electrons. So those are the ones on the inside. And the ones on the outside are the valence electrons. And so those are the ones that change. So if we look at the periodic table, carbon is in group 4A. It has 4 valence electrons. The noble gases are in group 8A. All of them except helium have 8 valence electrons. Oh, look, here's a picture. So these guys all have 1 valence electron. If we look at their electron configurations, just the highest part, the highest N, sodium's 3s1, lithium's 2s1, hydrogen is 1s1. In the groups, the electron configurations end the same way. Carbon is 2s2, 2p2. Silicon right below it, 3s2, 3p2. The difference is that these electrons are in a next higher principal energy level. But carbon has 4 valence electrons. It also has 2 1s electrons, but those are on the inside. So the highest principal quantum number for carbon is 2. So we're going to count the electrons in the second level. For silicon, it's 3. So the reason that elements in these columns have similar properties is because they have the same number of valence electrons. But Mendeleev predicted this when they didn't even really know what electrons were, much less how they were arranged. Write an electron configuration for phosphorus. Identify the valence electrons and core electrons. How many electrons does phosphorus have? 15. 15 electrons. So without drawing orbital diagrams, 1s is first. We'll fill that up with 2. And 2s2, 2p6. Now we're up to 10 electrons, right? Then is 3s2. And it's 3p3. So that adds up to 15. You can check yourself by adding the superscripts. The superscripts should add up to the number of electrons that you were trying to indicate. So here's its electron configuration. Which of these are the valence electrons? The 3s2 and the 3p3. The ones in the highest n. N1, n equals 2, n equals 3. Any of the levels with n equals the highest number. The highest floor that has people staying on it. Those are the valence people. Okay? Here we get to the good part. I should really rearrange these slides and put this earlier, but the periodic table can actually be divided into blocks representing these 4 different orbitals and the quantum sublevels S, P, D, and F. The number of columns in a block corresponds to the maximum number of electrons, and the row number is equal to the highest principal quantum number. So let's look at this. You see this block of elements?
Yeah.
And it's 2 columns wide. That represents S electrons. The S subshell can hold 2 electrons. Look at these pink guys over here. How many across? 6. The P subshell can hold 6 electrons. The yellow ones in the middle here, 10. Those represent the D subshells. You can put 10 electrons in the D subshell. And these guys represent the F block. So you can actually look at the periodic table, understanding that, and you can just pick an element and rattle off the last term in its electron configuration. So let's try this guy. antimony. So I'm going to look at this. He's 5, and this is the P block, so it ends in 5P, 1, 2, 3. 5P3. Magnesium, 3. This is the S block, S1, S2. Argon, 3rd level again, in the P block, 3P6. That one's all full. So you can imagine going across, here's 1 electron, it goes into the 1s. Helium, okay, helium and hydrogen, they are the babies of the element family, and they just break the rules, right? So they're just little exceptions to everything. Because for this purpose, helium should really be over here, because there's a block missing. But helium is a noble gas, and the reason that helium belongs over here is that first energy level is full. And all of the noble gases have their valence shell full, and that's really important. But there's 2 electrons, 3, the third one goes into 2s, and then 2p, and then the fifth one goes into 2p. And so the order is hidden here. 1s, 2s, 2p, 3s, 3p, 4s. This is 3d, because we didn't do 3d yet. And the way I think of this is, imagine that this part used to be up here. Wouldn't that make sense? Just going down, la-di-da-di-da, down a step here. And it sank. These are d orbitals, but they really kind of belong up here. They're 3d. The reason they're down here is because they're higher in energy. Lower in the table means those electrons are higher in energy. They're higher in energy than the 4s because of all those interactions between all these electrons. So that's how I remember that this is 3d. So 3d, this is 4p, 5s, again this is sunk, 4d, 5p, 6s, this is 5d, and then these guys are sunk twice, and so this is going to be 4f, and 6p, 7s, 6d, 5f, and 7p. So whichever way makes more sense to you, go with that. But I like the periodic table.
Why are there different configurations in the D block?
The D block, so these parts that stick up, which represent elements that have valence electrons in the S and P subshells, these are the main group elements, and they are very predictable. These guys are the transition elements, and they are not predictable. All sorts of weird things happen, and we're going to talk about some of them.
But on this element, we don't have like the 3, like the scandium, we don't have like the 3s2. We have like 4s2.
Right.
Are we supposed to?
Because they do funny things. Okay. This is 4s2 because this 4s is full. And the next electron, this is the D. And this goes D1, 2, 3, 5. And this is 4s1, 3d5. And we're going to look at why that is. Yeah, it does weird things. We ignore that in Chem 3A. 1A, we have to talk about it. So this is a different way of looking at it without all that stuff in the middle. The P, D, S, and these guys are the F block. And the numbers here for S and P correspond to the principal quantum number. For D, you have to take this -1. For F, which these guys fit in right here, it's n-2. So use the periodic table to determine the electron configuration of bismuth. Bi. Well, we got to find it first. It's down here, right? So using the periodic table and the noble gas configuration makes it really easy. So let's do the noble gas configuration. What we're going to do is we're going to go up a row and find the previous noble gas. It's xenon. So we know that this is the same as xenon, but it's got some other electrons on it. So there's xenon, and then what is added? Well, 6s2. And then this part is what? 5d. And how many electrons are in there? 10. Now, do you see this little gap in the arrow? See, this goes 57, 58. We can't ignore these guys. They're cut out. We should take the periodic table and cut it with a pair of scissors and put these guys in between. It makes it too long for a piece of paper. And we don't use those guys much anyway, so they put them at the bottom. So these are the F. So this is the 6th row, so this would be 4F. And how many are there? 14. And then we get to the P. This is back to 6 again. 6P3. Isn't that kind of cool? A little. But it's all in the periodic table. And the periodic table was made before we understood how the electrons were arranged. I just think that's amazing. Just awesome. Periodic table is just crazy cool. So there's irregular electron configurations. The 4s is lower than the 3d, so the 4s fills before the 3d. But the difference in energy there is not very big, and so some funny things happen with the transition elements. Some of them have irregular electron configurations. So we get the ns being only partially filled before the d, or not filled at all. And those electron configurations are determined experimentally. We can kind of look at them and try to make some sense out of them. Here's chromium. We expect it to be 4s2, 3d4, but it's actually 4s1, 3d5. How many electrons can the d subshell hold? 10. So this is half full, and the s is half full. And there's something special about the level, the subshells being half full. It's like some weird special that the hotel is running. That if you get the S and the D rooms exactly half full with people, will give you a discount. And so the guy from the 4S room says, "You mean I can jump up to the 3D room and have my own bed, and it's going to cost me less? Hey, let's do it, right?" That's what the electron people do.
How would that be presented in a problem?
They'd say, write the electron configuration for chromium, and they would expect you to remember.
What do they expect us to remember these?
Are you going to remember for the test?
You're going to have to remember.
It's just these 5? Or
The top 3. So you should know these guys. Molybdenum. But these guys are doing the half full kind of pattern here. So 4s2, 3d4, by bumping one of these 4s electrons up to the 3d, we get 2 subshells that are half full. What happens with copper is here we have the s completely full and the 3d is almost full. And it's slightly lower in energy if the 4s is half full and the 3d is exactly full. So there's a benefit in there. And then ruthenium and palladium are just a little harder to predict and remember, and that's why I'm not going to ask you to do them. But you should know those first 3. Okay?
And it's only these?
Only those 3 that you have to know.
No, but I'm saying those you have only those.
No, there may be more. I'm not gonna commit to that. We could look at the chart, but I don't feel like it.
Okay.
Yeah, they're squirrely.